This video covers section 10.6, which is the counting principles, permutations, and combinations. And so these are basic tools that we have to learn to be able to solve probability questions. So, and by the way, 10.6 is probability. That is the title, the one that we're doing on Friday. So right here, just a very simple example. If you were a person, a guy, who has two pairs of jeans, let's say black jeans, blue jeans. Oops. Okay, I cannot write on it. Okay, so you have those two, and then you have three different shirts, tan one, white one, and a blue one. So how many combinations can you make with those? Well, you can combine your tan shirt with blue jeans, yellow with blue, and your blue shirt with blue jeans. But since you also have another pair of jeans, you could also match those with the black pairs, with the black jeans, right? So how many combinations you have total so far from here? Six, right? So two pairs of pants, and three shirts. But now if you include your shoes, because you have two pairs of shoes, a pair of black shoes and a pair of red shoes. So if you include those with this single outfit here, you could get two more outfits, right? Because of the shoes. And then if you mix and match, you can get another one, but we're not going to get into that. So then here you get, from this one outfit, you get two more outfits, and so on. So then at the end, if you count all of them, how many different combinations do we have? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, yes. And so this is a very simple example of what the fundamental counting principle is. And so the number of ways, why can I write over? So the number of ways in which a series of successive things can occur, found by multiplying the number of ways in which each thing can occur. So for example, for this one, we have pants. How many options for our pants? 2, right? And then how many options for our shirts?
6.
Only 3. 1, 2, 3. And then how many options for our pants? I mean our shoes. 2. So if we multiply 2 times 3 is 6 times 2 is 12. So that is a way to find what the total number of possibilities will be. Okay? Now let's get to example 1. Have any of you guys seen Clueless, the movie? It's from the 90s, not too long ago. Clueless. Do you remember at the beginning when she like has her closet in a computer and then it matches her outfits? So something like that, you know. If she was to ask how many possible outfits I could get, it would be done by the counting principle. Now let's think about your options when you plan a schedule, because we all know you have many possibilities, right? Especially when there's only one class being offered. So for this one, it says you're planning to take 3 courses. So we're going to have 3 spots: math, English, and humanities. Based on time blocks and highly recommended professors, there are 8 sections of math. There are 5 for English, and there are 4 for humanities. So that you find suitable, assuming no scheduling conflicts, which is, you know, is like saying assuming no air assistance, right? That's impossible. So assuming no scheduling conflicts, how many different 3-course schedules are possible? 160. 160, thank you. So 160 combinations of those classes, assuming they don't overlap or whatever, which is not gonna happen. All right, multiple choice test.
It has 10 questions.
Where's the 10 questions?
Oh,
Each of the questions has 4 answer choices, with 1 correct answer per question. If you select one of these 4 choices for each question and leave nothing blank, in how many ways can you answer the question? So let's see, how many questions do we have?
10 questions.
10. 4, 5, 6, 7, 8, 9, 10. Okay, and then we have 4 choices, right? So we're gonna be multiplying 4 times 4 times 4 times 4. So 4 to what power? 10. And that is the answer. Now, I remember when I learned this the first time, I used to get confused if it was like 10 to the power 4 or 4 to the power 10.
Those are 2 different numbers.
Correct. So then the way I learned was just to not please, but at first I would like just write them like that so that it could make sense in my mind that it was 4 to the 10 power. So what is the answer, guys?
1,048,576.
48,576. Yes? Okay. So that is the possible ways. So can you, and how many ways can you guess all of them right? Only one way. So what is your probability that you will get by guessing at 100? 1 over a million. That's like literally, that's what it is. Okay?
Most tests these days have like 60 questions.
There you go. All right, now our next test here, 6 questions, and they have 3 answer choices. So it's gonna be 1, 2, 3, 4, 5, and 6. And then we have 3 choices per question. So it's gonna be 3 to the power 6. See that? What did I tell you? That's why I like to kind of like expand it, because if it was 6 to the power 3, you're talking about only 3 questions with 6 options. Yes. 6 to the power 3 is 3 questions with 6 options each. How can we write 6 questions that are true or false? 2 options per question, right? And how many questions did I say? 6. So 2 to the power 6. It will be 6 questions. Write this down because on your homework you might have something like that. 6 questions, true or false. Okay? This is 3 questions with 6 options right here. And this was the 6 questions with 3 options each. So, does anyone have a number for that? 3 to the power 6?
729.
Thank you.
Bringing it down earlier.
All right, now let's go to the next slide. See, this one is pretty easy, right?
But it's gonna get hard.
No,
I expect it to be.
not really. It's a little bit.
Bad.
Okay, the next one is actually very, very interesting because I've been reading on it. Telephone numbers in the United States begin with 3-digit area codes, followed by 7-digit local phone numbers. Area codes and local telephone numbers cannot begin with 1 or 0. How many different telephone numbers are possible? And so, for the area code, we have to, and this is that we're assuming that we're just calling in the U.S., okay?
Yeah.
Because everyone knows that if you're calling from, let's say, from Mexico, there is an international code, a country code. What is that? 1. 1 is the international code for the U.S. What is the one for Mexico? 52. That's the country code. So each country has their own code.
The US number 1, though. That's weird.
I think they just appropriated that. Okay? So for the area code,
We will only be number 1.
we have to exclude 1 because then it's like we're already using this. Okay? Now, why do we have to exclude 0? Does anyone remember dialing 0 ever?
Isn't that an operator?
Yes, that is the operator. I don't know if they still exist. Okay? So then for your area code, the first number, how many digits are there from 0 to 9? 10 digits, okay? Because we include 0. So out of 10 options, we take 2 out, so you have 8 options. And then for this, you have 10 options. Can we start a phone number with a 1?
No.
With a 0?
No.
So 8 options. And then the other numbers, it doesn't matter. There we go. So we're going to have 8 to what power?
8 to 1.
Well, we have 2. So 8 squared. And then 10. How many 10s do we have?
You have 1, 8,
8. So go ahead and type that on your calculator. Okay, let's revise your answer. So I got 6 billion.
6.
No, and then 400,000.
Multiply. Oops.
No,
60.
400 million. So 6,400,000,000. Thank you.
6.
Yeah, 1, 2, 3, 1, 2, 3. Yeah, so 6,400,000,000. Okay. What is the population of the U.S. expected to increase by the year 2020? Do you guys remember that problem we did, like, with geometric sequences? Yeah, so I have the number here, don't worry. So,
Wasn't it like 5 when we wanted a 4?
it's 223 million. Or is supposed to, hold on. Okay, so let me read this from the book. By the year 2020, portable telephones used for business and pleasure will all be video phones. At that time, U.S. population is expected to be 323 million. Faxes, beepers, cell phones, computer phone lines, and business lines may result in certain areas running out of phone numbers. Solution: add more digits. With or without extra digits, we expect that the 2020 video phone greeting will still be hello, a word created by Thomas Edison in 1877, who was the phone inventor. Inventor Alexander Bell preferred Ahoy, but hello won out. Okay, nice. So anyways.
How else were we supposed to greet each other exactly? What was supposed to replace hello?
I don't know, I've always found it odd. Like in Spanish, who knows how to answer the phone in Spanish? Bueno, like that makes no sense, right? It's like, what's good? I don't know. Okay, anyway, so this is why, for example, in New Mexico, in the whole state of New Mexico, I believe they only have 2 area codes for the whole state. But in New York, just the city of New York, they have like 5 area codes just for one city. Yes.
Thanks.
What is our area code here? 915. Yes. What is one of the ones in New Mexico?
417.
571. No, I'm sorry, 575. That's one of them that I know. Okay, so let's see this license plate, which could also become an issue, right, if we run out of numbers. So license plates in this particular state, they have 3 numbers and 2 letters. So how many different license plates could be manufactured?
27, no, 26, yes.
So for numbers, the 3 numbers, how many options do we have? 10 times 10 times 10. But here we're not being restricted, right? We can have a 0, we can have a 1, we can have a 9. And then letters, is
Isn't
it
it like 26?
26, right? Okay, so let's multiply that, guys.
26 squared times 10 to the third.
26 squared times 10 to the third, yes. Do we have an answer?
676,000. That's not a lot.
676,000.
It says one state, but it's the first state.
Okay.
Well,
It's
you never know.
That's reasonable. But what could this town do if they want to double their options, but not increase the number of letters or numbers?
The combination.
Combination. Think about this, David.
Hold another license plate.
Steel?
The one in front?
Let's think about the commutative property. Would it be the same to put the numbers first or the letters first? It will give you another plate, right? So then I will do that. And in fact, I've seen that done in Juarez. Like some plates start with the numbers, others start with the letters. So that could potentially double their options here if we just change the order. That's what I was saying, commutative. Okay, so let's go to the next one. Oh, I have to write a definition. So permutation. Okay, so a permutation is an order arrangement of items that occurs when one of them, no item is used more than once. So no repetition.
Unique values.
What do I mean? What?
Finding unique values.
Yes, we will. We will. And then the next one is the order. This is very important, guys. The order of the arrangement matters. And so the notation that we use is here. They both look like a subscript. So N, capital P, and then R. And what it means, it is the number of permutations of N things, they could be people as well, taken R at a time. Okay. So when I was telling you in the previous section that and choose R, that is not this one, okay? In fact, that one is going to come up in a minute. And it's going to be what we call a combination for that. Let's just write down the definition. Okay, so a combination occurs when,
There's still a definition on the back too.
yeah, we'll get back to it. So let's write this one. So the items are selected from the same group. That's one. Two, no items are selected oops, sorry. No item is used more than once. And third, the order of the items makes no difference. Okay, so this is the one that is the same steps as what we did with when we were doing the binomial theorem right here. The and choose R. That's why I was calling it that way. So going back to it, it doesn't really matter the way that you take your items out for a combination. But when we talk about a permutation, the order matters. That's why I wanted to define both at the first, and then we'll go back. So let's go back. So if I tell you the order matters in a permutation and the order doesn't matter in a combination, and which one do you get more options? When the order matters or where the order doesn't matter?
Where the order doesn't matter.
Okay, so let's see. Let's look at this one. So if I tell you the order doesn't matter, and I ask you how many ways can you order the letters A, B, C, D? Right? So you have 4 and you choose 3. So according to that formula that we did with the binomial coefficient, oh, I forgot. Okay, so 4 choose 3. And I'm going to use the same formula that we used with the binomial theorem. So it was 4 factorial, and then 3 factorial, and then 4 minus 3 factorial. So we would get, let's say 4 factorial, 3 factorial, and then 4 minus 3 is 1, right, from here? So 1 factorial. So this is 4 times 3 factorial, and here we have 3 factorial times 1 factorial. So the 3 factorial cancel, we have 4 over 1, which is 4. So we actually only get 4, because we just have A with a B and a C, A with a B and a D, A with a C and a D, and B with a C and a D. The order doesn't matter. But if I take this one, an A, a B, and a C, and I change the order, I'm going to get how many more? You get 6, right? Just by this one.
Oh, okay.
Now, if I take a B, and a D, but I say the order matters, A, B, D is not the same as A, B, B. Oh, oops, I read the same. ABD, ADB, BAD, BDA, DAB, BBA. So how many do we have? Another 6. 6, right? Then from here, we get another 6, because they're the same 3 letters, but I'm changing the order. So the order matters, Shelby. And then we get another 6 from here. So how many do we have total?
24.
24, right there. So there are only 4 combinations, but there are 24 permutations. So you actually get more when the order matters. Let me give you guys a very good example. Imagine that you are running to be a member of the SAC committee. Do you guys have positions there? No, right? You guys are just members of the committee. So will the order matter? Will the order matter? No. But what if you're running for president, vice president, and what's the third one? Secretary and treasurer. Will the order matter then? Yes.
Yes.
Yes. So that's a very good example. Okay, so going back to permutations. How do we know when that order matters? One example that the book uses a lot is the baseball, like the order of the batters. Does anyone play baseball here? No? Okay.
How?
All right. So the order matters because whoever goes to the bat first or last, it has to be like a good bat. So that's an example of it. We're not gonna discuss it since you guys don't know anything about baseball. Okay. So you and your 19 of your friends have decided to form an internet marketing consulting firm.
20 people.
Yeah, you probably shouldn't. The group needs to choose 3 officers, a CEO, an operating manager, and a treasurer. Do you guys think that matters? Who's the CEO? Yeah, so order matters. So that's how you know you have to use permutation. So we have out of 19, we're going to take 3.
It's 20.
No.
You and 19 of your friends.
Oh! I thought the answer was 20. So 20, and we're going to use this formula because the order matters. So it's a little different than the combination one, but not too different. We take 3, correct?
3 rolls.
Okay, so we got 20 factorial, and then on the bottom, with combination, we used to take the small number factorial and then the difference factorial. But this one, we only take the difference, 20 minus 3, and then factorial. So that's going to be 20 factorial over 17 factorial. So this 17 factorial, I want it here, and then it's 18, 19, and 20. So I cancel my 17 factorials, and I get, can someone multiply 20 times 19?
6840.
So that's
6840.
6840. Okay.
I think you just wanted to say it. You didn't understand.
All right, now the next one, we have a corporation has 7 members on its board of directors, and how many ways can they elect a president, vice president, and secretary and treasurer? So we need to take 4 out of 7. The order matters?
Yes.
Yes, and in fact, I shouldn't be using this symbol. Let me correct myself. I should not use that because that's for combination. That is reserved for combination. So I should be writing it this way. Out of 20, we take 3. So then here, out of 7, permuted with 4. So it's going to be the big number factorial, and then on the bottom, the difference of the numbers factorial. So 7 minus 4 factorial. So this is 7 factorial, 3 factorial. So this is 7 times 6 times 5 times 4 times 3 factorial over 3 factorial. So let's just multiply those.
840.
840. Very good. Okay, so let's move on. You need to arrange 7 of your favorite books along a small shelf. How many different ways can you arrange the books? Assuming that the order of the books makes a difference to you, like if you're OCD or something. So again, we have 7, and we're going to arrange them in 7. Yes. So let's see how many ways we can order them because the order matters, right? So 7 factorial over the difference of them, 7 minus 7 factorial, so 7 factorial over 0 factorial. So we have 7 factorial over 1. What is 7 factorial? 7 times 6 times 5 times 4 times 3 times 2. Remember, did I show you where to find factorial symbol?
Yes.
So you go to menu, and then probability, and then it will be the first one.
You can also just click the.
Yeah,
Yeah.
yeah.
The exclamation button, which is next to the letter G. Thank you. So what do we get? 7 factorial? Come on, guys.
5040.
5,
40.
50,
54.
5,000. All right, we're gonna skip 5 because it's exactly the same way. Let's see. We already got that definition, correct? So let's look at those 3 examples and see if we need a permutation or a combination, okay? Which one is the one where the order matters?
Permutation.
Permutation. So you need to remember that because you're gonna be like, oh, which one was it? Permutation. Yeah. Okay. Order matters. Okay, so the first one, 6 students are running for student government. President, vice president, and treasurer. I think that's enough, right? What is that? Permutation or combination? Permutation, because of course everyone wants to be the president. Permutation. Okay, 6 people are on a board of supervisors for your neighborhood park. A 3-person committee is needed. Only a 3-person committee to study the possibility of expanding a park. How many different committees could be formed from 6 people? Combination, because assuming the people in the committee have the same say-so, right?
No matter who makes a committee, as long as they study this part.
Right, Baskin Robbins offers 31 different flavors of ice cream. One of its items is a bowl consisting of 3 scoops of ice cream, each a different flavor. How many such bowls are possible?
Combination.
Combination. Unless you have specific.
A banana split.
A specific
committees that
taste.
have
I say, like if you put it in a cone, I will have a preference,
Yeah.
right?
Yeah.
But if it's
Taste good with
horizontal,
the
maybe not. Okay, formula for combination. So,
We even have a Baskin Robbins out here. I haven't seen one.
yeah, we do.
Yeah, the right one.
What now?
Yeah.
In that one area, it's like all the dentists and the dogs and is it Franklin? Is that where it is? Franklin, yeah.
Okay, so now let's compare them both quickly because we're almost out of time. So we already went over the problem with the letters, right? So here we got 24 options and here we got 4 options. So what's the difference? How can I go from a 24 to a 4? I need to divide by 6. Now let's see where that 6 comes from. So that 6 give me a sec. Okay, yeah. No. Okay, yes, I got it. So the formula for combination right here, it will be, well, that's the one we did. And then for permutation, it will only be, okay, let me write the formula, expanded version. So it's 4 factorial over 3 factorial. Oh, that's where the 6 comes from, where the thing there. And then 4 minus 3 factorial. When we go to the permutation formula, we only take 4 factorial, and then we do the subtraction here, the 4 minus 3 factorial. So the one that makes that division divided by 6 is from here. That's why you get less options with combination. Less with combination because the order doesn't matter. But that's also because you're dividing by a bigger number. And with permutations, you get more options because your denominator is smaller. All right, so we'll stop here, but I'm actually going to record the last slide, and I need you guys to watch it. Okay? I'm going to put it on the mode. So let's move on to example 7. A 3-person committee is needed to study ways of improving public transportation. And how many committees could be formed from the 8 people on the board of supervisors? And so in this case, I can write it this way, 8, and we are going to choose 3. And it is a combination because we're talking about a 3-person committee. The order doesn't matter. So in this case, we're going to need the formula that we take the 8 factorial, the big number, and then we get the difference here, 8 minus 3 factorial. So this will be 8 factorial over 5 factorial. And so this will be 8 times 7 times 6 times 5 factorial over 5 factorial. So here we cancel those out, and we get 8 times 6 times 7. And that will be, oh my gosh, and I'm actually doing the wrong thing because for combination, I'm also missing the 3 factorial. My bad. So we have a 3 factorial here, 3 factorial here, and I also know that 3 factorial is equal to 6, so I can cancel those. And now my answer is just 8 times 7, which is 56. Okay, checkpoint 7. So from a group of 10 physicians, in how many ways can 4 people be selected to attend a conference on acupuncture? And so in this case, 4 people, it doesn't matter who was chosen first. So we're going to do a combination again. So we have 10 physicians, and they're going to send only 4 to the conference. So in this case, I'll do the correct formula, I promise. So it's 10 factorial, 4 factorial, and then the difference, 10 minus 4 factorial. So in this case, we have 10 factorial, 4 factorial, and then here 6 factorial because 10 minus 4 is 6. So here we have 10 times 9 times 8 times 7 times 6 factorial over 4 factorial, 6 factorial. So that goes out. And I will leave that answer for you to find because I don't have it with me. So let's go ahead and move on to the next one, which is a very, very nice transition to our section 10.7, which is probability. And you guys know a little bit about cards. So let's review this one. Why is this called a royal flush? Well, because all the cards have the same suit. And then also because we have them in order such as straight. So ace, king, queen, jack, and I believe this is a 10. Yes, 10. So you have a straight, they're all of the same suit, and this is the highest possible straight you can get, so that's why it is called a royal flush. And by the way, a royal flush, it beats 4 of a kind. So let's see, in poker, a person is dealt 5 cards from a standard 52 card deck. And we already know that you're going to have 13 of 4 different suits. So you have 13 hearts, 13 diamonds, 13 clubs, and 13 spades. So those 13 make the total of 52. So how many different 5 poker hands are possible? So this is going to be a 52, and you choose 5. And so here we're going to have 52 factorial over 5 factorial, and then we're going to have the subtraction 52 minus 5 factorial. And so this will turn into 52 factorial over 5 factorial, and 52 minus 5 is 47, so we'll have 47 factorial. So in this case, we can expand it this way: 52 times 51 times 50 times 49 times 48 times 47 factorial. And so I do that because I want to cancel it with the 47 factorial that I have here. However, I still have 5 factorial on the bottom. And so the answer for that will be 2,598,000 960, and that's the answer. So this concludes the video.